Hi there, folks. Today we're looking at graphing rational functions. And remember, rational functions are functions that are expressed as a fraction. We've already looked at the graphs of one of these things, and we've talked about the components of the graph, but now we're actually going to start graphing these. And we're going to do this from two different perspectives, okay? We're going to do it from the perspective of transformations, of kind of translations, sliding things like moving them left, right, up and down, stretching them and shrinking them, which should be a concept that's familiar to us from previous functions that we graphed. Remember, the idea is that once I've seen one of these functions, I've pretty much seen all of these functions, but they look slightly different depending on what I do to the function. It moves things depending on what I do to the function, all right? The second way we're going to graph these is kind of going from the perspective of figuring out the components of the graph, finding the vertical asymptotes and the horizontal or oblique asymptotes, finding the holes in the graph, and then going from there, then graphing the function and maybe doing a little bit of an XY chart. Okay, either one of these methods is not going to be 100% accurate. We're not going to memorize patterns like we did with some of our other functions, but they're going to be accurate enough to make sure we have the asymptotes in the right spot and generally have a curve that represents what we want. Okay, so if you recall, the graph that we've looked at previously is the most basic form of this thing, which is the y equals 1 over x. And when we graphed this thing, it gave us a representation of what rational functions look like. We see these two curves that kind of go off hugging these asymptotes in different directions, all right? And we have that value that's undefined. And there's a couple of things that are really important about this graph. The first one is this vertical asymptote right here is x equals 0. The second one is the horizontal asymptote right here at y equals 0. And it's important to understand that a vertical line is an x equals, a horizontal line is a y equals. We have those lines graphed as dotted lines. That kind of gives us 90% of what we need to graph this function. All right. The other thing we need is the general location and kind of the general curve of this thing. All right. And again, every function, every other rational function is going to kind of look like this guy, but maybe in a slightly different manner. All right. If you recall previously, we had methods for graphing where basically if we were to add or subtract certain things in certain places, it moves the graph up and down or it moves the graph left and right. And then if there was a certain value that we would change, it would tell us whether the graph opens up or down. It would tell us whether we're going to stretch or shrink. And that's no different here. Like if I modified this function and said, hey, I'm now going to do y equals 1 over x minus 3, that would move the function down 3 units. Or if I changed this guy to a plus 5, that would move the function up 5 units, but I'd have the same graph. If you recall, if I continued to kind of modify this function, if I did something like y equals 1 over, instead of just x, if I did x plus 8, that would move this function to the left 8 units. And if I did something like y minus 6, it would move the function to the right 6 units. All right. And if I modified it further, if I put a plus 1 here, that would move this thing to up 1 and to the right 6, but we draw the same graph. And that's kind of some of the stuff that we've done with previous functions. Here's the a value for us. Instead of a 1 here, if I change this guy to a 2, it's going to stretch the function vertically, all right? If I were to put, and here's where it becomes a little bit tricky, if I were to put something like a 1/2 here, that would shrink the function vertically, but see, that would actually be written as 1 over 2 times the x minus 6. That's how we would write a fraction within a fraction. Does that make sense? And the idea here is that we're doing the same things that we've been doing to other functions. It's just a little bit more complicated here. Okay, so it might seem like it's a little bit different, but it's the same kind of stuff. And like if I were to change this guy to a -1, well, that would flip us vertically. So all of a sudden this curve would be up here and this curve would be down here. It would trade places. All right, so it's all that same stuff that we've been doing. All right, except it looks a little bit more complicated because we have a more complicated function. All right, but we're going to kind of try to keep this as simple as possible when we go through this. So I'm trying to erase this without erasing too much. There we go. And so if I kind of look at this, if I look at this guy, See, this first one's in the format that looks like 1 over x has been modified. And that's kind of what we're looking for, okay? If it looks like 1 over x has been modified, we want to do the approach of taking the 1 over x function and moving it around and stretching it and shrinking it and do all that kind of stuff, okay? If it looks like the kind of function we would normally factor and simplify, then I want to do the approach of finding the components like we did the other day, all right? So this one, it looks like 1 over x has been modified. That plus 2 means we're going to take the same function and we're going to move it up 2 units. So if you recall, the other function had a vertical asymptote right here at x equals 0. And that doesn't change because if I move that line up or down, it's still that same line. But we had a horizontal asymptote at y equals 0, that's going to move up too. So now you see the horizontal asymptote is going to be here. Okay. So again, when you compare it to the previous function, look at where that vertical and horizontal asymptote are. See, the horizontal asymptote is here. I've now moved it up 2 units. So instead of being at 0, now it's at 2. All right. But now I'm going to draw the same basic graph because this thing is just like the 1 over x function. Basically, the graph is going to look the same. It's going to have pieces over here that look kind of like this, and it's going to hug this line and then hug the other line. And it's going to have some pieces over here that kind of look like this, and it's going to hug this line and then hug the other line. And that's it. All right, we draw it the same way, but we've moved it around a little bit. And again, most of this is just identifying, hey, here's the vertical asymptote, and here's the horizontal asymptote. All right. If I look at the next one does not look like 1 over x has been modified. It looks like something that's a little bit more complex. It looks like one of those things that we might try to factor and simplify, all right? And if we run into that, it means we want to approach this thing from finding the components. So now I'm going to find, any vertical asymptotes or holes in the graph. I'm going to find any horizontal or oblique asymptotes, all right? For example, this one, I always start with the domain, so let's talk about the domain restrictions. For this one, it's x can't equal 0, okay? And then from there, I would try to simplify this thing. So like I would factor the numerator denominator. This one, I can't factor the numerator. I can't factor the denominator. And it looks like nothing cancels out, so that one's as simplified as it can get. So remember, we identify vertical asymptotes and holes in the graph based on what canceled out. Okay. Remember, removable versus non-removable restrictions. If I look at the second version of this thing, if I look at the second equation I wrote, the domain restriction of x equals 0 is still there. It has not been removed. So that's my vertical asymptote. The hole in the graph comes from any domain restriction that got canceled out. But since nothing canceled out, I don't have any hole in the graph. So now I got to look at horizontal or oblique asymptotes. And to do that, I have to look at the degree of the numerator and denominator. Here, the degree is a 1, and here the degree is a 1. Since the degrees are the same, it's going to be a horizontal asymptote. And it's going to be y equals, I divide the leading coefficients. Here, it's 2 divided by 1, which is a 2. And that, remember, is pure memorization on this guy, okay? So now I have the vertical asymptote right here. X equals 0. There it is, a dotted line. Y equals 2 is my horizontal asymptote. That's right here. And when I'm doing in this format, the easiest thing to do now is just to do an XY chart to figure out where these curves are. So I pick X values that are kind of near the vertical asymptote. So that's at 0. So I pick a -1 and a +1. I just choose a value on either side. If I plug a -1 into the function, that gives me 2 times -1 is a -2, plus 1 is a -1, divided by -1 is a +1. If I plug a 1 in, 2 times 1 is a 2, plus 1 is a 3, divided by 1 is a 3. So I get these two ordered pairs. I get this guy down here, and I get this guy up here. What that's telling me is I have a curve down here that goes through that point and hugs these lines. And I have a curve up here that goes through these points and hugs these lines. And that's it. And see, the interesting thing here is when you look at these two functions, when you look at the graphs, don't those graphs look identical? And they should, because this is literally the same function, but in the two different formats that we might see it. And you're probably thinking, well, the first one was a lot easier to graph because it looked like the 1 over x function. And you're absolutely right. It's easier when we can just move this thing to find the components rather than finding the components on our own. Okay? But here's why they're the same. You ready? Let me draw a little thought bubble here. They're the same because if you were to take these two things and get common denominators, see, that's 1 over x. The 2 you have to multiply by x over x. See, that's 2x over x. Now I have common denominators. I add the numerators. Denominator stays the same. And notice that is the function that's written over here. Okay? And so anytime we have this in the function of 1 over x, it can be written in the other format and vice versa. Okay? So keep that kind of stuff in mind. This guy, same kind of thing. If we look at this one, this first one is kind of in that format 1 over x, but it's been modified. This guy right here tells me to move this thing up 2, just like the last one. So that's going to put my horizontal asymptote right here at y equals 2. But then right here, this minus 3 right here tells me to move the function to the right 3, which means instead of having my vertical asymptote at 0, it's going to go to the right 3, and it's going to be here instead. And then the effect that that 2 has is it stretches this thing vertically a little bit. So what happens is I'm going to have a slightly steeper curve than I would have had previously. Okay, so instead of having, something like, the values of 1 here, it might stretch it a little bit. Okay, so I'd get something that looks more like this. Instead of having a value of 1, I might have a value of 2 here. And so I kind of get the same thing, but it stretches it vertically, which almost takes my curve farther away from those two lines, where those two lines intersect. Okay, but I get basically the same function, but the curve is slightly different. That's it. I'm moving the thing around. If I look at this other one, the perspective is this. I have to say, okay, what's the domain? So in this one, the denominator can't equal 0, so the domain is x cannot equal a positive 3. And then I would simplify. So like this one, I might factor the numerator. The denominator doesn't factor any further. And then I try to cancel out. Well, here, nothing cancels out. So that means my domain restriction is going to be a vertical asymptote, x equals 3. Since nothing canceled out, I don't have any holes in the graph, so there's none of those. And then I have to look at horizontal or oblique. Go back to the original function right here. A 1 and a 1, when the degrees are the same, it's a horizontal asymptote. And I divide the leading coefficient, so it's y equals 2 again for this one. All right? And so as I start to plot this thing, watch this, x equals 3. That's this guy right here. Y equals 2. That's this guy right here. And now from here, I would do an XY chart to figure out where to draw my curves. And you're probably already realizing that this is the same as the previous example, but in the other format, okay? But again, since my vertical asymptote is at 3, I'm going to choose a 2 and a 4. I'm going to pick one value on either side and then just plug it in. 2 times 2 is a 4, minus 4 is a 0, divided by negative 1 is a 0. And then when I plug a 4 in, that's 2 times 4 is an 8, minus 4 is a 4, and then in the denominator 4 minus 3 is a 1, so that gives me a 4. So now I just plot these 2 points. 2, 0 is right here, and then 4, 4 is right here. That just gives me an idea of how far away this is, and kind of gives me an idea of the curve. So draw your curve, go through that point, and you're just hugging the lines. Okay? Every rational function is going to kind of follow the same format. It's going to look similar to this, all right? But here they are in the two different formats. If it looks like 1 over x has been modified, you just move the thing. You shift it left, right, up, and down. You stretch it and you shrink it. But if it looks like one of the ones that we would simplify, you have to find the components. And ultimately, the ones where you find the components are probably a little bit more difficult. So we'll do a couple more of those examples with a little bit that are a little bit more complicated, okay? For example, if I look at this guy, all right, so Again, we're just going through this process of finding these different pieces. So let's start with the domain. You have to factor this thing in order to find the domain. So let's factor this thing completely. Here I factored out the 4. That leaves me with an x minus 4. In the denominator, I build a bridge. That factors into an x minus 4 and an x plus 3. And now from here, the domain, x can't equal 4 or a negative 3. And that's just from setting the denominator equal to 0. And now I simplify this thing. Ready? This time it simplifies. These cancel out. And that's a little bit different than any of the examples we've done so far. This one's a little bit more complicated. But now think about what the new domain restrictions would be for your simplified version. The only domain restriction I had for the simplified version would be x can't equal a negative 3. So when we talk about removable versus non-removable, it looks like the negative 3 is still a restriction, so that's my vertical asymptote, is x equals negative 3. The 4 that was a domain restriction is no longer listed when I get to the simplified version, so remember that's our hole in the graph. And remember, that's just the x value for the hole in the graph. You have to plug it back into this guy to get the y value. And so when you plug that 4 back in there, it looks like you get 4/7. And now horizontal or oblique, you have to look at the degrees. Here, the degree is a 1. Down here, the degree is a 2. When the denominator is bigger, it's horizontal, and it's automatically y equals 0. Okay? And so now I go to graph this thing. I start with the asymptotes. Ready? I've got a vertical asymptote at negative 3. I have a horizontal asymptote at y equals 0. And now from here, it's just a matter of finding out where these pieces are. Do an XY chart. Let me take it off to the side. And make life easy on yourself. Again, when you do the XY chart, use the simplified version. And notice I have the vertical asymptote at negative 3. I'm going to pick an x value from each side, negative 4 and negative 2. Okay? And so again, I'm picking one on each side of this thing, right here and right here. Those are the two x values I'm searching for. And again, plug them into the simplified version here. All right? So if I plug a negative 4 in, negative 4 plus 3 is a negative 1. 4 divided by the negative 1 is a negative 4. If I plug the negative 2 in here, negative 2 plus 3 is a 1. 4 divided by 1 is a 4. And see, that just kind of gives me a location for this thing. It says, okay, negative 4 is right here. And really, since this thing is symmetrical, if you just kind of look at these lines, you also have a point that's here. It gives us kind of this idea how far away this curve is. Okay? Up here, same kind of thing. Negative 2, 4. Be right here. And then think about where this guy would be in terms of being symmetrical to that thing. We'd have a point here. All right? And we just kind of draw a curve that hugs those lines and goes through the point. Okay? But the fact that that thing is not closer to this value here, like the first one we ever graphed, that point was here. Now it's up here. It's stretching my curve away from that kind of intersection point. All right? And then the last thing we have to do here, and most of the time I would do this beforehand, but this time I'm doing it after. I have a hole in the graph at 4/4. So if I go to the ordered pair, 4/4 is right here. Instead of having the curve continue, I just put an open dot right there to show there is a hole in the graph, and that's it. Okay? So make sure you go back and plot the hole in the graph. If I look at this next one, again, same kind of thing. Ready? I'm going to factor everything completely. Denominators, difference of squares. But now let's think about the domain restrictions. And I have to identify those before I cancel things out. So x can't equal a 4 or a negative 4. And now simplify. These guys cancel. So the simplified version of this thing is y equals x minus 6 over an x minus 4. And now again, kind of before and after. So I do the domain before, and now I think about the domain after I reduce. If I were to ask the domain of the simplified version, you would say x can't equal a 4. So now look at it. Which domain restriction stuck around? Which one's still there? The x equals 4. So that's a vertical asymptote. The one that's not there anymore is the x equaling the -4, so that's my hole in the graph. And again, that's just the x value. I plug it back into this guy to find the y value. -4 minus 6 is a -10. In the denominator, -4 minus 4 is a -8. So -10 over -8, I can write it off to the side. I would write that as a decimal or a mixed number makes the most sense. If you want to reduce this first, you can. But something like this, that's a 5/4. So that's a 1 1/4 or 1.25. Just because graphing is going to be easier if we look at it that way. Okay. And now look at the degrees. The degree of the numerator is a 2. The degree of the denominator is a 2. So that's going to be horizontal. And I find it by dividing the leading coefficients. Here's a 1 and a 1. So it's y equals 1. And so now I can start graphing this thing. Vertical asymptote at 4. Horizontal asymptote at y equals 1. And now I just have to do an XY chart to kind of help me figure out where these curves are supposed to go. And again, my vertical asymptote's at 4, so I'm going to pick a 3 and a 5. I pick one on each side of this thing. If I plug the 3 in, 3 minus 6 is a -3. 3 minus 4 is a -1. -3 divided by -1 is a +3. If I plug the 5 in, 5 minus 6 is a -1. 5 minus 4 is a +1. So when I divide those, I get a -1. And so I plot this 3, 3. And again, oh, sorry, I missed a little bit. We can kind of see the spacing of that thing. Going to kind of give me something that looks like this. The other value, 5, -1. So 5, -1 is right here. Again, same kind of spacing. And you can plug in more ordered pairs if that makes you feel a little bit more comfortable. And then the hole in the graph, I can't leave that. -4, 1 1/4. So -4, 1 1/4 is about here. So I just locate the spot on the graph that's supposed to have a hole in it, and I draw a hole in the graph. That's it. All right, last one here. Again, I factor everything completely. So I say this guy factors into an x minus 3 and an x plus 2. This guy I can't factor any further. So now domain x can't equal a 1. I simplify, but again, nothing cancels this time. So before and after, the domain has not changed, which means this guy is a vertical asymptote. Nothing canceled out, so I don't have a hole in the graph this time. And now I have to look at the degrees to figure out horizontal or oblique. The degree of the numerator is a 2, the denominator is a 1, so this one's going to be oblique this time. And I find that by doing synthetic division. So here I go. The 1 goes in my box. I write down my coefficients. I bring this guy down and I multiply and I add straight down, and I multiply and I add straight down. And so this interprets it as y equals 1x plus 0 and then minus 6 over the thing I was dividing by. But remember, I just get rid of the part that doesn't look like y equals mx plus b. So it's just y equals 1x. That's the equation of my asymptote. And so now I graph these things. X equals 1 right here. Y equals 1x. That has a y-intercept of 0 and a slope of 1. And so the big difference here is I have an asymptote that's not a horizontal line. It's a diagonal line. I'm still going to hug one of those lines. And so it modifies my function just a little bit more than I'm used to. But now I go to the same place. I say, hey, you know what? XY chart. And once again, I pick a value from each side of that vertical asymptote. So I'm going to choose a 0 and a 2. And you can plug it into the original, or you can plug it into the factored form here. But if I plug the 0 in, I get -6 over -1, which is a 6. If I plug the 2 in, let's see, that's 4 minus 2 is a 2, minus 6 is a negative 2, over 1 is a negative 2. And then I plot each of these 0, 6, and then 2, negative 2. And again, that doesn't give me a whole lot of information, but it's enough for me to say, all right, let me just draw a gentle curve that hugs each of these and goes through that point. There we go. Hugs each of those lines and goes through the point. And that's it. Okay, so find the different components, graph the asymptotes, find a point, and draw your curve.